coal-based economy of South Africa, because platinum group elements are very expensive. So there's also a lot of chromium and vanadium and a few other minerals which are found in this bushveld igneous complex. And it's basically a suite of igneous rocks, and there's 3 different types of igneous rocks that formed in a massive sort of underground basin, igneous chamber basically, and you had different injections of melted magma into this chamber, and different rocks crystallized out. And today some of these are exposed at surface, and so we're going to have a look at this. So this is this geological map of South Africa, and the area we're zooming into today is just north of Johannesburg and Pretoria, and the rocks that we're looking at in particular are these green ones here, and some of the purple, and then they're also around here, and there's a little bit of green up there near where Petersburg is. So this is where the bushveld igneous complex rocks outcrop today, and we believe that these are the rocks on surface today, that they're all linked underground, and it was all part of this enormous underground magma chamber 2 billion years ago. So this is zooming in to that part of the map, just looking at the bushveld igneous complex rocks, and there's basically 3 rock types. So at the base of the sequence we have the Rooiberg group, then the Rustenburg layered suite, which is in green, and which is the most extensive, and this is where the reefs that are mined are, with the platinum group elements and the chromites. And then the sequence is capped off by the Leboa granite suites, and these rocks are shown in pink and are at surface. So here's Pretoria. So going north of Pretoria, a lot of the rocks that you find at the surface are part of this Leboa granite. It's also used a lot as dimension stone, like kitchen tabletops. So it's beautiful kind of pink granite, which you will have probably seen in someone's kitchen. And then as I said, we believe that this is all part of an enormous magma chamber, and only some of the edges basically are exposed at surface. So we've got these younger rocks in light yellow, which cover over some of the surface of this igneous complex. So to look into more detail at this, we believe that there are basically 3 stages of formation. And so the Rooiberg are these rhyolite eruptions. So rhyolite is a type of lava, and they basically form on top of the Transvaal supergroup. So we had done the Witwatersrand supergroup, then the Transvaal supergroup, and so the Rooiberg is directly over that. And then the next part of this layered intrusion is the Rustenburg layered suite, and this is a basaltic magma which intruded underneath the Rooiberg, and it crystallized very slowly. So basically how geologists imagine this formed is that in the earth you have this molten lava which comes up and fills an enormous magma chamber, and you have different injections of molten lava coming up into this magma chamber and basically pooling out. So you have these pools of molten rock, of magma, sitting in this magma chamber, and as this begins to cool very slowly, different minerals crystallize out and form. So you've got individual basically crystals as this magma cools slowly, and it's all still underground, and as it's cooling these crystals form, and then they very gently sink down, and you form basically layers as these crystals fall out. And as these crystals come out of solution, the magma that you're left with, the composition of that changes. So it becomes relatively enriched in other minerals as you crystallize these minerals out. So at a later stage, you start crystallizing out a different type of mineral. And then all these little crystals also begin to sink down, and you build up another layer. So this is the kind of theory behind what's happening in this magma chamber, that you have different minerals forming and crystallizing and settling out and forming layers, and then that your magma sitting in the chamber is then changing in composition, and you get a different type of mineral, and this process continues and continues. And when we start to look at the rocks, you'll realize how incredible this is and the scale at which this has happened. So that's the Rustenburg layered suite, and that's the most important part of the Bushveld igneous complex, and it's where the ore minerals are. And then the youngest rocks that make up this complex are the Laboa granites, and they've then intruded kind of to cap off the sequence. And this all took place during a relatively short geological window. So it's still kind of millions of years, but in geological time it's relatively short, yes.
Also to the western, the Royberg.
I guess because the Royberg lavas are pretty strong, if you have a look at this picture, so it's complicated. It's not just a simple layer cake. The Rustenburg layered suite is, but how they all fit together is more complicated. So the first, the youngest rocks is this Royberg group, and they're in orange, and they're actually towards the top here. So they were formed first. Then the Rustenburg layered suite formed underneath them here in green, and this is covering an enormous area. And it's incredible how these layers persist out across this area. And then the Laboa granites came and intruded in between the two. I guess it was at the contact between the two there was a weakness, and the lavas then intruded into there. So they're not in stratigraphic order because the youngest is actually squeezed in between the oldest and the middle one. So that's basically a cross-section through the Bushveld igneous complex, just looking at how the different rock units fit together. And then we've got the other supergroups that we've already looked at. We've got the granite basement in pink, the Karpval Kraton, the Witwatersrand supergroup, the Ventersdorp supergroup, and the Transvaal supergroup. So those should all be familiar to you, and they are forming underneath the basement rocks, and then the Bushveld igneous complex is sitting on top of them. So the BIC is Bushveld igneous complex for short, and this contains more than 85% of the world's platinum group elements. And they're listed here: ruthenium, rhodium, palladium, osmium, iridium, and platinum. Yes?
Proportions. Say 78% of the world's platinum.
Yeah, so this is what economic geologists do. So it's a field of geology where resource estimation. So economic geologists work out how, and it's just basically looking at the geology, like in one of these reefs, how much chromium is there, and they do a resource estimation for that mine and then for the whole complex, and then compare this to what we know for the world. So yeah, I mean, it could be 76%, or, so there's a little bit of wiggle room, but basically, yeah, a lot of work goes into. And this is important because these companies are listed on the stock exchange, so they have to have a pretty good idea of what they're actually worth. So, yeah, that's a lot of the world's platinum. And platinum is a very important mineral, not just in jewelry, although the jewelry trade for platinum is enormous, but it's used in fuel cells, and there's a huge growing market for platinum. And South Africa really controls the world platinum market. A colleague of mine said the reason that platinum jewelry is so expensive is because the reason women like it is because it's more expensive than gold. But anyway, so South Africa produces around $3.8 billion of export revenue a year from platinum. So it's a major part of our economy. And other resources in the Bushveld, there's chromium, vanadium, iron, and tin, and also copper and other base metals. So it's basically this incredibly rich resource of minerals. So the chromium there's two main reefs that are mined for their minerals. So the chromium is mined from two reefs which are called the upper group 1 and 2. So UG is upper group 1 and 2. And this is just giving you an idea of what these rocks look like. So you can see the chromite. So this is almost pure chromium forming these black layers. And then in between the white is anorthosite. So that's the mineral plagioclase. So it's an almost pure plagioclase rock. So to form these layers, and as you can see, they're quite amazing layers. It's this process that I was talking about here, where you've got almost pure chromium crystallizing out and then settling down. And then the composition of the magma changes and you get another mineral forming. And basically this just keeps changing and alternating, and you get this layered suite, which is all crystallized out in a magma chamber. And the UG2, so the upper group 2 reef, is the one which is particularly mined for the chromite. And the chromite reef can be, over a meter thick. It's quite an amazing sort of geological phenomenon. And there's also platinum group elements kind of locked into the chromium. So it's mined for both of those. Then the other reef that's mined, and the other important part of the Bushveld complex, is called the Merensky Reef. And this is particularly mined for its platinum group elements. And the rocks are a norite, which is a type of igneous rock. And it has chromatite again and sulfides. So you can see the kind of coppery looking sulfides, and that's what has the platinum group elements bound in it. It also contains gold and copper and nickel as byproducts. So incredible mineral wealth in this reef. And it's 30 to 90 meters thick, so up to almost a meter thick. So there's different strategies of exploiting these reefs, kind of depending on their geological setting. So where these rocks outcrop at surface, they can be mined and surface. And this is the Sandsloot open cast platinum group mine, which is 30 kilometers north of Mokopane, which used to be called Petersburg. And this is basically just an enormous open cast mine. These trucks here, for scale, are enormous mega trucks. The wheels of these trucks are a story high. So it's just to give you a sense of scale. This is an enormous open pit mine. And this is where particularly the Merensky Reef is on the surface. And so it's possible just to mine it on surface and do this enormous open cast mine. But most of the mining of the Bushveld Igneous Complex is done underground. And this is an example of so many of the mines are around Rustenburg, where the UG2 and Merensky reefs are mined. And incredible yields, 280,000 ounces of platinum a month. And the thing with these reefs is that they're relatively narrow, from tens of centimeters to maybe a meter depth of the reef, and that's the rock that you want to mine and extract out. So to keep this profitable, particularly where you're having to mine underground, you don't want to be mining out huge volumes of rock. So something that's really being developed in South Africa is narrow reef mining. So this is extra low profile mining, where you just go in and take out as little as possible of the surrounding rock to just get your reef. And this is a photograph here of an underground mining, and you can see from the floor to the ceiling it's only just taller than these miners. So they're doing extra narrow profile mining. And these are very dangerous conditions to mine in. And so another thing that's happened, particularly in South Africa, and it's been really developed in the platinum mining industry, is mechanizing the mining. So using special low-profile machines to go into these narrow reefs, to break the rocks and to put roof bolts in to make it safer. So it's often places where it's very dangerous for people to go in. They've been able to send machines in. And South Africa is kind of leading the world in this narrow reef mining mechanization. Yes.
Moving layers of rock, what will that do to like the top? I mean, if you're going below and to that, isn't it going to?
No. Well, we really hope not. So I mean, the whole premise of mining is that you go in underground and you take out some rock, but then you have to support the overburden, basically, because that's exactly what you don't want, is for it to collapse. So they put in special I don't know if we can see any here. They put in special supports basically to hold it and to bracket it. And the idea is that you're taking out a relatively small amount of rock, that you won't get a collapse, that the sides are strong enough. And they'll never clear out absolutely everything. You leave pillars of rock and put in supports. All right, so I've got a video to show you. It's a little bit long, but it gives you a very nice explanation. And it gives you a very good overview of the Bushveld Igneous Complex and how it formed. And it's also really nice to see this narrow reef mining in action. So I hope this works after the other day that they didn't work. The music is a little bit dramatic.
Largest and most important repository of platinum group metals. It extends laterally.
So the green is showing the rocks on surface.
It was formed by volcanoes that repeatedly injected molten basaltic rock known as magma or lava into a huge subvolcanic chamber inside the Earth. The cooling and solidification of the molten magma resulted in the formation of igneous rock. Because the molten rock was beneath the surface of the Earth, it cooled much more slowly than usual. By slow cooling, different minerals crystallized at different temperatures, and with time, cooled magma forces of the Earth caused the layer in the middle, giving them the shape of thin saucers. The central part semicircular. These outcrops are referred to as the Eastern Limb, from Sierkoi-Gat through to Steelpoort, Leidenberg and Stoffberg. The Western Limb, from and the Northern Limb at Potgietersrus, now called Mokopane. The Bushveld to beyond the west, and 250 kilometers from north to south, that dips towards the center. As early as these are the and their true magnitude does not as yet appear to have been realized. The Bushveld not only, but also the regularity of the layering of its mafic and today contains the world's richest known deposit of platinum-bearing ore, including ore metals as well as base metals and gold. There are three different ore of the Bushveld which platinum is extracted. The first ore reef has a 0.25 to 1 and is well mineralized with high platinum group metals or PGM. It also contains base metals such as copper and nickel. In the only reef that was mined.
Okay, so here you can see this support here behind, so the guy's drilling, and what he's doing is he's drilling holes into the rock, which they'll put explosives in to blast and detonate and break the rocks off to literally mine them. And just this thing here behind him, that's what's holding up the roof of the mine. And it's really narrow. You can see the miners crouched down because they're only mining something that's just, a meter thick. And it's to keep it as profitable as possible to do this narrow, really narrow mining. So in the old days when they were mining the Witwatersrand supergroup, the reefs are thicker, and they would just kind of go in and take everything out. But with this platinum mining, to keep it as profitable as possible, they've done this narrow reef mining.
Approximately 10 tons of Merensky ore, the equivalent of 1 ounce of platinum. The second ore body is the upper group 2 or UG2 reef. The UG2 is a thick chromite seam with a width of 0 and 4 depending. It contains most of the PGMs and lean in base metals. Identified in the 1920s, no attention was initially given to this potential ore body until the 1970s. It had a way of new metallurgical technology in the concentrator process. The UG2 reef is not and is much the Merensky is not viable. Has already been mined. Approximately 20 tons are required. The UG2 chromite reefs can both be traced on the Earth's surface for over 300 kilometers. The extends over 30 kilometers and has a thickness of all its primary ratios for nickel, Merensky and UG2 reefs. The platinum mine, PPL, has been operating on the Platte Reef since the 1990s. Nearly today, his prophetic words that the platinum discoveries in South would transcend in magnitude and importance anything that has hitherto been dreamt of. Still, the vast expanse of South Africa's
slide, the one that mentioned the ounces per year of platinum. Okay, so in the video they mentioned that you need 2 tons of the ore to produce 1 ounce. That proportion translates to like 2 million tons.
So it's an amazingly sophisticated underground system. So most of these mines operate 24 hours a day. They have a day shift and a night shift. And they normally do the blasting at night because there's fewer people underground. And then every morning the geologists go down. The first shift normally starts at 6 in the morning and the guys are underground at 6. The lifts go down. And then the geologists will go out and look at the newly blasted faces. Well, they blast and clear those rocks overnight. And they have hoppers, they have basically underground trains to collect the ore, and they have these special low-profile diggers that you saw them in the front-end loaders in the movie, and they've been specially engineered to be as low-profile as possible. And they collect up the ore and put it in the hoppers, the trains, and then they'll have a series of lifts which bring it back to the surface. And then first thing in the morning, the geologists will go down and look at the new face, and you saw that guy painting the white lines. So that's what mine geologists spend their lives doing. And what that geologist is doing is he's just marking the reef, and then the geotechnical guys will go in and mark where to put the new blasting, and then they'll spend the day drilling, and they you can see they had quite sophisticated machinery to help with the drilling, and drill holes in and then load those, and another team will come and load those with explosives, and then they get basically everyone out and blast, and the cycle continues. So yeah, it's incredible volume of rock that's basically been. And the resource estimation for the bushveld is that there's enough there to keep going for at least another 100 years of mining. So it's quite difficult to kind of wrap your head around the extent of it and the volume of rock that's been taken out. So any other questions about the bushveld? Okay, we've got a little bit of time left, so I'm going to start the next thing we're going to look at, and we'll have to finish it off tomorrow. We're not going to finish it today. So we're looking back at our map of South Africa, and we keep working through geological time And you can see up here, I hope looking at this map, you're beginning to pick out things which are familiar. And you can see up north of Pretoria, there's the Bushveld complex. You can see there's the western and eastern and northern limbs, those green and purple rocks. And what we're going to look at next is situated down here, south of Joburg, just in the Free State. Here.
General pattern to the age of South African rock. If you look on the map.
Not sure I understand. What do you mean?
On the youngest rocks left in one area, older rocks left.
No, it's not completely random, and I guess it's not totally ordered either. It's somewhere in between. So the oldest rocks are best exposed. They're all around here, so starting from just south of Swaziland, and those are the pink rocks. That's the edge of the Karpval Craton with the greenstone belts, which we looked at near Barberton. And then, so that's the Karpval Craton, which is then all subsurface as well. And then I guess you have the different basins that formed on this craton. So we haven't gone south, basically. We've stayed up in this northern part of South Africa, all the old rocks. And that's because South Africa that's all there was this small craton, which was all up here. And then as basically South Africa grew, then I suppose to answer your question, then yes. So we stay up here, and then the Cape supergroup rocks, which are all down here, this purple is the Cape supergroup, which is the next big thing in time. And then after that is the Karoo supergroup, which is all of these rocks here, which cover the most of South Africa. And I guess as the rocks get younger and younger, they've had less time to be eroded, so they're better preserved. And then the youngest, this bright yellow all over, are the youngest rocks in South Africa, which we don't have a lot of. So yeah, it's not completely random, but it's not as simple. So yeah, I mean, if you wanted to go from oldest to youngest, you would start up here and basically work your way across. And the colors, the color code of the rocks of South Africa is basically done by age. So the Archean, the oldest rocks are all down here, and they are ordered in this map by age. Maybe they should have done a rainbow or something to make it more logical. But there are certain conventions with the colors of rocks. Okay, so the next thing we're going to look at is the Vredefort Dome, the Vredefort impact structure. So this is almost exactly 2 billion years old. So it's just after the Bushveld complex in time. And what it is, it's one of the few geological phenomena that's observable from space. And it's a crater which is over 300 kilometers in diameter, and it's the largest meteorite impact structure in the world. And it's been partly eroded and covered with younger rocks. So if we look today, this is satellite imagery, and you can see there's this circular section here, and these rocks here which are forming the rim of a crater. So you have to, we'll come back and look at this, but this is what we see today, which is called the Vredefort Dome. So this is a geological map of the same thing. So you'll notice this is the town of Vredefort in the center, and we have this central part, and then these various rocks which you could see on the satellite image forming the rim around this crater. But you'll notice the scale here is much smaller. This is kind of 30 k's across. But we believe this is basically a remnant of a much larger structure that was over 300 kilometers across. And then if we look at the rocks that are shown in this geological map, we have in the core of this crater, this dome, we have the granite basement, which is the Karpval Craton basement. And then we have in the two oranges, the Witwatersrand supergroup, so that's here. These two, then we have the Ventersdorp lavas, which we talked about, and then they're overlain by the Transvaal supergroup, so the Tunispoort in blue and the Pretoria in pink. So those are all the formations that we've talked about so far. All the rocks are exposed in this sequence. and then the southern part is covered by younger rocks. Yeah.
Impact metamorphosis.
Just hang on. Just sit tight. So these rocks are called the collar rocks, and they form a ring of hills. So we've got the dome in the center, and then to the north and west, these collar rocks form basically this ring of hills. And the quartzites, so the layered quartzites from particularly the Pretoria group, are dipping towards the core, but they're young away from the core. So what's happened is that these quartzites, and this was the first place the geologists recognized it, have been completely overturned. And then they went and looked closer at the sequence. And yeah, all the rocks have been overturned, and we'll look at this in more detail. So what geologists believe has happened here is that this is the remnants of an enormous meteorite impact structure. And that 2 billion years ago, a meteorite the size of Table Mountain smashed into South Africa and would have created this enormous meteorite impact crater, which was over 300 kilometers long, and would have caused kind of massive widespread destruction and a magnitude 14 earthquake. So it was a pretty serious event. And these are basically some cartoons of the stages of impact crater formation. So at the top panel, you have the actual impact, and while this is, a little meteorite, the meteorite would have been the size of Table Mountain. It was not a trivial size thing. And you get this zone of intense compression and deformation, and then the impact, the shock waves travel out from this. And then as this shock wave advances, you get a rebound, and you get material being blown out, kind of catastrophically blown out from the impact. And the final stage is that you've had this initial impact and then the shock wave moving through, and then you get a rebound where the central material basically rebounds up into this hole created by the impact and the kind of shock of the impact. And this model explains what we see at Vredefort. So this is what we see in the Vredefort dome. So we have this central uplift where we've got the oldest rocks from this granite basement, which have uplifted in the center. And the collar rocks, so we've got the sequence, we've got the Witwatersrand, the Ventersdorp, and the Transvaal sequence. And so you have to imagine these would have all been lying here as nice layers, and then it's had this massive meteorite impact shock, and you've had these collar rocks have been completely overturned. So the sequence that we see today at the surface, they've been basically flipped over. So the Vredefort impact structure has been observed for a long time, and geologists didn't initially agree with each other as to how this formed. So there's been various evidence for it having an impact origin. So that's what you were asking, that we should see some evidence for this. And one of the key pieces of evidence is a rock called pseudotachelite, which is the product of this impact. And from the huge kind of addition, it's basically frictional melting. So the rocks get shocked and melt instantly and basically form this black glass. And there's a couple of other things that you can look at in a meteorite impact. One are shatter cones, where you get actual shatter through the rock and it preserves these very specific structures. PDFs, which in this case are planar deformation features, and this is on a microscopic scale. So individual crystals of quartz shatter in a very specific way, and you get these planar deformation features on individual crystals. And you get specific high-pressure minerals which form from this the shock metamorphism. So this pseudotachelite, which is a black glass-like material, and it has rounded to angular fragments of the surrounding rocks. So this is formed basically from that huge meteorite impact where some of the rocks have been instantly melted, to form this black glass, and you get other fragments which haven't quite melted. So this is a picture of a quarry near Vredefort, where you can see the black rocks with these fragments of the original granitic basement sitting in them. And here you've got fractures which are filled with this pseudo-tachelite. So the fact that they found a lot of the pseudo-tachelite in the main part of the Vredefort dome was a clue, basically, that it was of meteoric origin, or from a meteorite impact. So these are shatter cones. So this is in the Hospital Hill quartzite. So these quartzites are part of the Witwatersrand supergroup. And you can see there's a penknife and a pen, so something about that big, and we're looking at a scale kind of this size. And this is from where that shock wave has gone through the rocks and basically caused these shatter features in the quartzite. And you get concentric conical surfaces, and as I said, it's from this intense shock wave. And these, if you plot them up, all radiate away from the center of the dome as the shock wave moves through these quartzites. And these are looking at the planar deformation features in the quartz grains. So these are from the gneiss, which is the metamorphosed granite in the central part of the dome. And this scale here is 0.1 of a millimeter. So this is really small. And you can see these planar features in the quartz grain, where an actual quartz grain has been shocked and preserved this. And this is another where we've got this grid-like pattern of shock damage in mineral grains. So if you take these rocks and make thin sections, you can observe these kind of features, which was another piece of evidence for a meteorite impact. So just to kind of wrap up, and we have had time to do this, what we believe happened around 2 billion years ago is that an asteroid the size of Table Mountain basically just smashed into southern Africa, and this would have caused an immense explosion, and we would have had an enormous crater that was over 300 kilometers wide. And this crater had overturned the succession of rocks that we understand have formed on the craton, and these are called the collar rocks, and they completely overturned, and the stratigraphy has been reversed. And then the central part of this impact crater then rebounded, and that's what's formed the dome of these granite basement rocks on top today. So this is the largest impact structure on Earth today. So although only a fragment of it has been preserved and is exposed today, we can work out that it would have been over 300 kilometers across, which makes it the largest and oldest meteorite crater. Yes?
Meteorite / asteroid.
It would have been completely destroyed by the impact. It would have basically just been vaporized. So the energy of this kind of, the whole thing would have taken place in 4 minutes. It's just completely devastating. And I think it's almost impossible for us to kind of imagine what it would have been like. But the asteroid, would have been the size of Table Mountain. It would have just been vaporized completely. And as I said, it would have been the equivalent of a magnitude 14 earthquake. So 2 billion years ago, there wasn't very much in the way of life on Earth. All we had ticking away are our friends, the cyanobacteria. So they would have been fried, basically. But there was no other life. If something like anything close to this had happened today, it would have probably wiped out life on Earth. So obviously the little cyanobacteria did survive because they persisted. But we can be, it's good it was 2 billion years ago. Yes? Yes, it's just basically completely vaporized by the impact.
So I'm assuming this hit the continental rock?
Yes.
The oceanic crust?
Yeah, that's a good question. It would have done the same thing and even more damage, and where it wouldn't have been preserved because that oceanic crust is being recycled because of plate tectonics. So there probably were other big impacts like this. We just don't have evidence for them today. The reason this one is preserved was because it was on a craton. Okay, so to look back at what we've done today and to talk about what we're going to do next. So we looked at the Bushveld Igneous Complex, this amazing igneous intrusion with incredible mineral wealth, which is the top part up there on the map. So I hope if you looked at a map of South Africa, you'd be able to pick out where it is. And then here, those semicircular rocks, those are the collar rocks of the Vredefort Dome, which is this massive meteorite impact. And so these things both happened at around 2 billion years ago. So what we're going to do, the next part, and what we're going to do tomorrow, is look at these rocks here, which are on the border with Namibia, and we're going to look at how we keep forming this, the rocks of South Africa, and keep building onto this craton. And then we're going to go up into Namibia and look at some rocks which aren't on this map, and these record a major change in Earth history. We're going to leave the Proterozoic. I'm going to look at the end phase of the Proterozoic and move into the Phanerozoic and look at the early evolution of life. So that's what we're going to do tomorrow. All right. Any questions? Everybody's all right. Okay. Thanks, guys. See you tomorrow.